I think because of the availability of the recording, many people don't care. They can access the recording and no need to, not interested to come in the class. Anyway, that's not a problem. Okay, I started recording. Okay, so as I told before, the bottom line of our current teaching, my current teaching, is basically to learn various experimental techniques to determine the rate determining step of a reaction. Any reactions that any reactions that can be a catalyzed reactions in presence of catalyst, or a normal reactions without a catalyst. Okay, so what is the rate determining step, and not only for that, what is the nature or structure of the transition state in the rate determining step. So what kind of experiment we can do easily in the lab to understand the reaction pathway. Okay, so first one we discuss about the order of the reaction. So order of the reactions can tell that definitely what is the rate determining step and what type of molecules of the starting material, what kind of or which molecules or which starting material molecules, and how many of that molecules are involved in the rate determining step or in the transition state of the rate limiting step, right? That order of the reaction can easily tell, and that is the first experiment we need to do to understand the nature of the transition state. Okay, the second one is Hemont postulate, but I thought I will discuss in the next class. Okay, I don't. I want to finish today slowly about the activation parameters, because this is more important than Hemont postulate. Postulate is the postulate, that is a proposed things. That is not an experiment. But the activation parameters is an experimental parameters. It is coming from experiment. So that I need to discuss a little bit about the theory. But I am trying to tell you in a pictorial way, not much equations, but there are a couple of equations. So let's go the first about the theory, and then I will tell what is the activation parameters. So activation parameters are actually coming from a theory that is called transition state theory, that we are talking about, right? Transition state, you know from the high schools that, okay, this is the transition state, A is converting to B and it is causing a barrier, and the transition state is associated with that molecule that is associated with the highest barrier on the top of the barrier, right? That is the transition state that we know from the high school. But this is actually coming from a theory, and that is called transition state theory, that was developed by Eyring. Eyring, I think he was an English chemist. His very famous Eyring equation activating parameters that I am teaching you, those are widely used in chemistry and chemical engineering to understand the reaction pathway. But unfortunately, he is one of the persons who actually didn't get the Nobel Prize, but he's supposed to get. There are very few cases, many famous persons, like including like Mahatma Gandhi, right? That they supposed to get Nobel Prize, either peace or science, but they didn't get it. But they're supposed to get it. Later, Nobel committee regretted that, okay, this person should get Nobel Prize, but for some reason they didn't get it. Right? So one of the person is Henry Eyring. So whatever we are discussing, that we will be discussing about the Eyring plot, and he proposed the theory about that. His name is transition state theory, from where the concept of transition state is coming. Okay, so the theory is based on a very simple equation. The A and B is giving the product. A and B is converted to product. So A and B is in equilibrium with a activated complex, that is actually the transition state, that is AB hash. This is a transition state, but there are some assumptions. Everywhere it is assumptions. Whenever you read the Schrodinger equations, I hope from the physical chemistry, right, in CML 100, every theory has some assumptions, every theory. right? Hooke's law, everything, classical mechanics, quantum mechanics, everything, every theory is based on some assumptions to simplify the theory. So this is assuming that A and B, this is actually not true, but still A and B is in equilibrium with a activated complex. Sometimes it is true, sometimes may not be true. Okay, depending on the what is the barrier in between the AB versus A and B. Okay, so but assuming this is an equilibrium, then the activated complex is giving the product. Okay, so this is the energy profile diagram. You can also assume that if barrier is low, then this is true that A and B is in equilibrium if barrier is low. Suppose this is a highly exothermic reaction, so A and B is converting to product. Okay, so this is the product. Suppose this is a highly exothermic, so product energy is much lower compared to A and B. And suppose here if barrier is less, then the transition state AB can be an equilibrium with A and B. Okay, clear? If you have any questions, please ask me. Or if I am going very fast, please also let me know. I will be slow down. So A and B is converting to the activated complex. So there will be a constant that is called equilibrium constant, right? Equilibrium constant. And when the AB has, that is the transition state is converting to the product, the second step, definitely that is also there will be also a rate constant that is small k has. Not has, this is called what is that? Okay, let's consider it as. Okay, it's the second rate constant. So first one is equilibrium constant, second one is the rate constant for the second step, or that is the converting the transition state to the product. So what will be the rate law? So it is very simple, right? Now we are expect to deduce the rate law. So rate law will be the rate equal to this K into AB activated complex, concentration of activated complex, right? It is here. Then what is the AB? It is in equilibrium with A and B. So K has should be the activated complex divided by concentration of A into concentration of B. So if you just then convert this one, so this is equivalent to equilibrium constant into concentration of A into concentration of B. Am I correct? Is it correct? Yes or no? It's clear?
Yes, sir.
Yeah, this is very simple, right? Very simple. So first is the rate constant, equilibrium constant, and second one you can consider as a rate constant for the reactions that is converting from the transition state to the product. So what is the overall rate constant? A, B, this is converting to P. So it should be, suppose the overall rate constant is K. A, B is converting to P. The overall rate constant is K. So if you just the first equation and second equation, if you just compare, then the overall rate constant K is equal to equilibrium constant into the rate constant for the second step. Very simple. Is it fine?
Yes, sir.
Any questions?
Yes, sir.
Yeah, it is very simple, right? So K is the overall constant, that is the A, B is converting to P is equal to the multiplications of the rate constant of the individual steps. The first step is the equilibrium constant and second step is the rate constant for the second step. So that's, you know that from Professor Saswant's course. It's very simple. Right. Okay. So this is the so far we have reduced the overall rate constant into equal to the equilibrium constant into the rate constant of the second step. Fine. Now the equilibrium constant, you can these equations you can deduce from the thermodynamics. If it is an equilibrium constant, so equilibrium constant, if you consider the K, so this is related to the del G, right? So del G of activation equal to minus RT ln K. Equilibrium constant, K is the equilibrium constant. So K is e to the power minus del G by RT. That you also know, I think from your high school also. Now it is within the high school syllabus. If you don't know, that is also fine. At least from CMP as well as Professor Sasandip's course, we have learned that equilibrium constant is equal to e to the power minus del G of activation divided by RT. So here we are not, this is not about thermodynamics. This sign is indicating this is the kinetic parameters, activation parameters. Okay. So del G is the Gibbs free energy of activation. Okay. Gibbs free energy of activation. So if you replace the equilibrium constant with this equation, then what will happen? The overall equilibrium constant K is equal to the rate constant of the second step into e to the power minus del G by RT. And what is del G of activation? We know that del G is equal to minus del H, right? Plus, this is wrong. This is wrong. Yeah, right? E to the power minus. Oh, no. It is correct. It is correct. There is another one bracket is there. Sorry. Sorry. Where is the eraser? Just 1 minute. Yeah. So this is correct because there is another one bracket is there. So del G equal to del H minus T del S. Right. So the overall rate constant K is equal to K has into e to the power del S by R into e to the power minus del H by RT. These are very simple reductions, nothing fancy, right? So what you are doing, K equal to K equilibrium, and this is the part is capital K equilibrium constant, right? Yeah. So if you just deduce, then K equal to K has into e to the power del S by R into e to the power minus del H has by RT. Right? Is it correct or not? This is fine. Did you get it?
Yes, sir.
Yeah, this is very simple. So del H minus T del S, that is coming from the Gibbs free energy at equilibrium. That you know that del G0 equal to del H0 minus T del S. Okay. Okay. So you can see here this equation, this final equation, actually this is similar to an Arrhenius equation, isn't it? This equation, the K equal to what is Arrhenius equations? What is Arrhenius equation? K equal to, can anyone tell?
K is equal to A e to the power minus EA by RT.
EA by RT, right? So you can see that this part K into e to the power del S by R, this is a constant or not? So assuming del S is constant for a reaction, changes of entropy, S is the entropy, right? R is constant, rate constant. So this is, you can consider this is A, okay, and this enthalpy you can consider this is equivalent to activation energy EA, right? So you can see this is actually similar to the activation, Arrhenius equation. K equal to A into e to the power minus EA by RT. So here EA is replaced with del H, enthalpy or activation energy, and A is the constant, and whatever the K into e to the power del S by R, that is also a constant. So this is actually a similar equations of the Arrhenius equations that I am telling here. Okay, right? So K equal to A, that is the pre-exponential factor, into e to the power minus EA by RT. EA is the activation energy. This is vague. What kind of activation energy is overall activation energy? Okay. And whatever we have deduced from the transition state equation, this is also a similar equation, A equal to e to the power minus del H by RT. So here EA is converted to del H. So it is similar, right? Rate constant. So whatever the rate constant we deduced from the transition state theory, this is actually the similar compared to Arrhenius expression. Okay, is it clear?
Sir.
Yes, it is. It is okay. Nothing. I'm not giving any complicated equations or nothing. It is very simple. Okay. So whatever we deduced from the transition state theory, it is not at all different. It is the similar or slightly like similar another form of Arrhenius equations that we have already learned from the high school. High school, right? All right. So let's deduce. So you can see here. So whatever the equations we deduced here, rate constant k equal to k has into e to the power del s by r into e to the power minus del h by r t. You can see here there are two parameters. We got a new parameters. One is del s of activation, another is del h of activations. Okay, these we got from the transition state theory. And this is a value. What is del S? There is the changes of activation. Changes of activation of entropy. Del H. This is the changes of enthalpy. So if is the A and B is giving to product, this is the starting material. This is the product. Okay. So whatever the del S, this is actually changes of, because this parameter you are getting from equilibrium constant, isn't it? So this is for second step. We are not considering the second step. Your barrier is coming from the first step. So whatever the del S and del H, this will influence for the first step. Okay, clear? So whatever the changes of del S means changes of activation. That is the changes of activation in between the transition state and the starting material. Whatever the changes of enthalpy, that is the changes of enthalpy in between transition state and starting material. Okay, because we are not considering the K here. K is the for next step. But for kinetics, to know the rate determining step, we are considering the highest barrier, right? This is the barrier. Second step is not the barrier. Barrier is here. Okay, is it clear? So we need to determine by experiment what is the value of del S of activation and del H of activation. Then I will tell that how del H and del S value will give a hint what is the nature of the transition state. That is the my main point, right? Why we are doing? Because we will do some additional experiment, and that experimental outcome will help you to understand what is the nature of the transition state of the rate determining step. That is the last goal. That is the primary goal. First and last goal, right? That we need to do some experiment so that will help us to understand the nature of the transition state. Not only for that, that will also help to find which is the rate determining step. That I'm telling from the beginning, right? So here I'm going to tell you that how these activation parameters, so these del S and del H, these are called activation parameters. Del H and del S. Enthalpy or changes of del S, del means change in between the transition state and starting material, del H and del S, and hash sign is that it is the activation in the activation kinetic part. I'm not talking about this part. No. I'm talking about only the kinetic part in between the transition state and starting material. Make sure it is clear. Is it clear? Hello, any questions? Any questions?
No, sir.
No, sir.
Please ask, please. So now from the transition state theory, we found two parameters, del S of activation and del H of activation. They are called activation parameters. Now we need to change this equation so that it will be helpful to get the value of del H and del S of activation by experiment, like similar to kinetics, right? So we have to deduce the equations so that it will help to find this the value of this parameter by experiment, right? So we need to deduce the equation for further. So for next steps we will change this k, that is the rate constant for the second step, and second step that this value will come from the Boltzmann distributions. Okay, giving this slide, Boltzmann distributions. This is the same slide I'm going to show. So here k, this is coming from k equilibrium, right, that I showed you in the last slide, e to the power del S by del S of activation by R into e to the power minus del H by R, and this is the second next important part, that is the rate constant for the second step, and that is coming from the statistical mechanics. I'm not going to tell in details. Okay, it is coming from the Boltzmann distributions from statistical mechanics. Okay, and this is the value. This is equal to k, that is called transmission coefficient, into kb. Kb is the Boltzmann constant, T is the temperature in Kelvin, and H is the Planck constant. Okay. Okay, and rest is the same. So k is the constant. Here everything is constant. K, kb, t by h. This is a constant. Okay, that is deduced from the Boltzmann statistical mechanics. Do you know Boltzmann statistics? Yes or no in physics? Have you read in physics?
No,
Boltzmann,
sir.
yes or no?
So the distribution curve a bit.
Okay. So this is coming from the Boltzmann distributions. Okay. So this is the equation overall. Okay. So how do you? Okay. Next is that if you just put ln k, so it will be the ln k kb by th. It is simple, right? Then it will be from here del h minus del h by rt, and this will come here plus del s by rt, right? Then if you just keep this t here, okay, so ln kb by t, so you can see this t, if you just put it down here, then ln k by t equal to del lh by rt plus, okay, it is here, so it is just revisit, okay, plus ln k dash by h, okay, plus del s hash by r. Okay, because this ln k, if you just keep it here, so it will be ln k by t. This same. This is same. This is same. And this is this. So it is k dot equal to k into kb. Okay, is it clear? It is just simply the reduction of the equation, the reformatting the equation. So this is called the Eyring equation. This is very famous. These equations will help you to determine what is the value of del H of activation and del S of activations by experiment. How do you find what is the value of del S and del H of a reaction? You need to do experiment. You have to do the experiment. And whenever you will do the experiment, right, you need to get a proper equation so that you can plot, and from the plot you can get this, similar to the plot how to determine the rate law, right, of a first order, second order, zero order reaction. So you can see it is quite obvious from this Eyring equation. If you plot ln k by t versus 1 by t, then it will be like a y equal to minus y equal to mx plus c. So if you plot ln k by t versus 1 by t, then you will get a straight line, right? So how do you know? So what? Okay, so let's do that first. So if you a plot of ln k by t versus 1 by t, then you will get a straight line with negative slope. So what about the slope? So whatever the slope you will get, or gradient or slope, that will be value of minus del h by r, right? This minus del h by r. R, you know what is the value of r, right? So if we just divide by whatever the slope into multiplied by r, then you will get the value of del H. It is very simple. And whatever the intercept you will get, that is the ln k dash by h. K dash is the already constant for a particular temperature. You can get it, and also from the R is the constant. You can get the value. From there you can get the value of the entropy of activation. Is it clear or not?
Yes, sir.
Yes, sir.
Yes. What about other people? I don't know who is telling yes. Yeah. Okay. If you don't understand, tell me. But I think as a chemical engineering students, this equations is nothing. All equal to y equal to mx plus c. You are better than you are much better than me in terms of math. Okay, I forgot all the maths. Okay, but that's I'm trying to present you in such a way that you can remember for a long time. Okay, in a pictorial way. But sometimes equation comes. I think probably this is the last equations in my course. Okay. These are Eyring equations, and this is all coming from the transition state theory. Whatever we are telling from the high school transition state, this is proposed by Eyring, and this is coming actually from the transition state theory. This is the actual theory from where we got the term transition state. Okay, yeah.
So, but as you told that the assumption over here was that the initial products and transition states should not have
Is
much
an
energy.
equilibrium. Okay, yeah, this is a special case, but this is the assumption you have to do, otherwise you can reduce. So if barrier is low, that is fine. Then it might be an equilibrium. Suppose it is a highly exothermic process. So the transition state barrier and the barrier of the static metal is low, then that will be equilibrium. But the same thing you can apply for other reactions, even though you have an equations. Okay, the assumptions. So some assumptions is needed to deduce the equation. Okay.
So what I was asking was
F3
that
is based on assumption.
the transition state term came from Eyring equation, right?
Yeah.
And now we use it for even normal case where the barriers might be bigger also.
Yeah. Now you are using as a common case.
Okay.
Assuming this is this. Otherwise you cannot deduce this theory.
Okay.
But good thing is that using one assumptions, you can easily get a equation that will helpful by experiment to determine the value of del H and del S. Okay, now tell me what experiment you will do. How you will get this plot? Okay, I also did it during my PhD, this plot. How do you will get it? Suppose you have 4 data points here, 1, 2, 3, 4. So what experiment you will do? What that experiment you will do is basically you have to first find the rate constant from the rate law. This is very easy. Suppose this is a first order reaction. So what you will do? ln k by t. Right, you get the linear slope, and from the slope you can get the k value. So once you get the k value, k will dependent on the temperature, right? Rate constant is dependent on the temperature. Am I correct or not? Arrhenius equation is also telling that k equal to e to the minus a by rt, right?
Yes, sir.
Yes,
So whatever the rate constant is actually temperature dependent. It is also told by Arrhenius equation. So what you need to do is here you need to determine that rate constant at different temperature. Suppose here you are taking 5 data points. So you need to determine what is the rate constant at 5 different temperature. Very simple. Suppose you are determining the rate constant at 23 degrees centigrade at room temperature. Another one you will take at 0 degrees centigrade, right? 273 Kelvin. It is Kelvin. T is the Kelvin. Another you will take at 373 Kelvin. Suppose 100 degrees centigrade. So you will take a range of 5 different temperature and find it. Do the same experiment, exactly same experiment. Okay, how to check how the reaction concentration of the substrate or product is changing with respect to time. That is the rate law. From the rate law, you will get the rate constant. Now you need to find the rate constant at a different temperature. Once slope, you will get the value of del H, and from the intercept, you will get the del S. So this is the experiment we do regularly as a chemist or chemical engineer. Is that clear or not?
Yes, sir.
Okay, Then I will go for example. So any questions other than couple of people who are always telling yes sir, that's good, but any other stupid questions?
Sir, is it like maybe a stupid question? Like, is it correct to interpolate the graph to the temperature 1/t equal to 0? Like, when we are trying to find the uh, when we are trying to find the intercept, we are actually keeping we
You
are
will not get
interpolating.
the intercept. Yeah, you will not get the intercept. Okay, that's a good question. Definitely not. Okay, because 0 Kelvin is not possible. That's why it's dot dot dot. Have you seen this?
So it's
So
one by
you have to
it is a,
extrapolate. So
so
your
but that would that be
yeah,
accurate? Because we can't even actually tell because this is 1/t. So when 1/t tends to 0, temperature would tend to infinity, right? So we can't even judge what will happen there. So is interpolating a good method to do?
why not? Why
So
not?
it,
I understand. Okay, suppose this is 1 by t, right? So you need to deduce this. Suppose it is the one data point is at 0 degrees centigrade. So it is 273 Kelvin. Okay, 273 Kelvin. So you get the value. You get the value. You get the value 1 by t. Then you have to extrapolate to get the intercept. Is it clear? That is a simple thing. You have to extrapolate here because you need to give the from the equations. This is the intercept. This is the value. Okay, so you have to intercept. That is dot 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 is here. Regardless what is this, wherever you will touch, that is the intercept. From that intercept you get y equal to mx plus c, right? So get the c value. But it is not 0 Kelvin. This is the 1 by t. Okay.
yes.
This is a routinely people do that. Yeah, and you will get a straight line. So only you need to determine what is the rate constant with respect to the temperature, because this is temperature dependent. This is temperature dependent, not only for these equations, also from the Arrhenius equations, you know the rate constant is temperature dependent, right? Or activation energy is also temperature dependent. Normally, if you increase the temperature, activation energy decreases. That's why reaction get fast. Normally, right? Because it increases the vibrations also. It increases the Brownian motions of the molecule. So if you increase the temperature, reaction normally get fast. Why? Because it decreases the energy barrier. That also influences the decreasing the rate constant. Why? Because molecules will be activated, bond will be highly excited, vibrations will increase, molecule will collide, it will increase the Brownian motions. That's why its activation energy or barrier get decreased on increasing the temperature. That is, everything is shown in the Arrhenius equation. Okay. All right. Now I think next 15 minutes I'm going to tell all about example, and you will find very interesting things with activation parameters. Okay. So activation parameters you can easily deduce from the rate constant or rate law. So whatever the first experiment, you have to always find what is the rate law. Then get the rate constant, then vary the rate constant with different temperature, and that's it. Okay. Okay, just 30-second break, then I'm coming.
So you are muted in case you are speaking something.
Okay, sorry, I don't know. Okay, so this is the first example that I'm going to discuss, and this same example I will discuss again and again and again. I discussed yesterday during the discussion about the red law. I'm discussing during the red in activation parameters again. I think every class I will discuss about this equation. So why? Because this experiment you will be doing in CMP 100. This is the one of the experiment in CMP 100. That is the acid catalyzed hydrolysis of ethyl acetate. Ethyl acetate plus water. I talked about this yesterday again today to give the acetic acid and ethanol. Okay. So what is the mechanism? This is a multi-step reaction. So you can see how many steps. The first step is that the catalyst, acid catalyst. I think from social lips course you know that this is a specific acid catalyst, general acid catalyst. So what is this acid? General or specific? What is this?
Specific.
Specific. This is specified with H plus. Okay. Specific H. This H plus will first bind to the oxygen and or the carbonyl oxygen, and it will increase the electrophilicity of the carbonyl carbon. This is first step, and this is in equilibrium. Then water will come and water will react to the carbonyl carbon of the ethyl acetate. We don't know what is the determining step. We will determine, but this is the proposed mechanism, multi-step mechanism. Then water reacts. So when water is reacting, this is one of the transition state. Then it gives the intermediate 2, right? And this is the plus charge because oxygen is already connected and binded to the carbonyl carbon. So now carbon is 4 coordinated. Then one of the OH will transfer here to here to give the intermediate 3. Okay. Then the ethanol will cleave using by this. This is the mechanism through a transition state, that is a transition state 2. Then ethanol will leave and give the intermediate 4. It's very simple, but you need to practice. Intermediate 4. Then again next H plus will leave and H plus catalyst will regenerate and it will give ethanol and acetic acid. Fine. So this is a multi-step reactions. 1, 2, 3, 4, 5, 6, 7 steps. This is a 7-step reaction. So how do you find that which step is the rate determining step and what is the nature of the transition state in the rate determining step? Okay. So first thing you will do is you will do the rate law. I am going one by one. Okay. In the exam question may comes. So do you tell me what type of experiment you will do, or maybe this is the red law or this, then did you deduce what is the possible mechanism, reverse way, either way. Okay. So this is the experimental result. I'm telling the answer. The rate is equal to K. This is the second order kinetics. This is first order with respect to ethyl acetate and first order with respect to water. So what does it mean? Whatever the rate determining step, both are involved. One molecule of ethyl acetate and one molecule of water is involved in the rate determining step. So which step might be? So it looks like this is the step, right? The water is attacking to the carbonyl carbon of ethyl acetate. If this is the case, then the kinetics will show this is the first order with respect to the water and first order with respect to the ethyl acetate. So that might be the transition state. This might be the transition state where both molecules are involved. Not only for both, one molecule of water, one molecule of ethyl acetate is involved in the transition state. So this pathway most likely the rate determining step. But one experiment you cannot tell. You need to find other experiment. Another one of the very important parameters to establish this transition state or the rate determining step is the activation parameter. That is our next experiment that I told you. So look at the active, there is the entropy of activation. So activation parameter consists of two parameters. One is the enthalpy and another is the entropy of activation. Entropy of activation. So entropy of activation, actually it gives more powerful hint compared to enthalpy. Enthalpy is also fine, but entropy will give more evidence about the proposed mechanism or proposed rate determining step. So enthalpy of activation, as I told, enthalpy of activation means what is this? This is the transition state. This is the product. So enthalpy, this is a change. Del. Del means this is a change. Del means the change. The difference between the enthalpy of transition state minus enthalpy of product. The difference. So what is the changes? What is the changes? What is the changes from starting material to transition state? So enthalpy of product, starting material minus enthalpy of transition state. What is the changes from beginning to the end? What is the changes? So if enthalpy is of starting material, okay, not P, suppose starting material. If enthalpy of starting material is more than the transition state, then what will be the changes? It will be positive or negative. If enthalpy of starting material is more compared to the enthalpy of transition state, then what will be the value of del S of activation?
Negative.
Negative means when you are moving from starting material to transition state, your enthalpy is decreasing. Enthalpy is decreasing means what does it mean? What is the enthalpy? Oh, I'm sorry, I'm bogus. I'm talking about entropy. What I'm talking about? I'm just telling. Okay, I'm talking about entropy, not enthalpy. Enthalpy will also change. Same thing is the entropy. Entropy is more powerful than enthalpy. First to study the mechanism. Same thing. What? Okay. So I am talking about del S. Del S means entropy. So if entropy of starting material is more than the entropy of transition state, then the changes of entropy del S of activation will be negative, right? What does it mean? If you found a del S of activation is negative, that means when the starting material is converted to the transition state, its entropy is decreasing. What is the entropy? Entropy is the randomness, right? The orderness or randomness. So if entropy of transition state is lesser compared to the starting material, that means the transition state is getting restricted. If there are two molecules of if there are two molecules of starting material, maybe two molecules are coming closer and forming a one molecule in transition state. That's why entropy is decreasing. And that is the case here. You can see here in the starting material, water and ethyl acetate are there. There are two molecules. They have more randomness, more entropy. But in the transition state, water is attacking and coming closer and attacking to the carbonyl-carbon, and it is giving a single molecule in the transition state. So its entropy will decrease or increase? Its entropy will decrease, right? Because two molecules are coming closer to each other. It is free in the beginning. It is free in the beginning. But in the transition state, the two molecules are coming close to each other. They are getting restricted and forming one molecule. So definitely its randomness is decreased. So its entropy will decrease compared to the starting material. Is it make sense?
Yes, sir.
Yes, sir.
Okay. So you can see that its value in the experimental value, it is negative and it is minus 26. So its value will give a hint about the mechanism. What is the rate determining step? What is going on? Okay, it is a very useful parameter to understand what is the nature of the transition state. So this huge negative value of entropy of activation indicates that there is a huge decrease of randomness from the starting material to the transition state in the rate determining step. That means two molecules are coming close to each other. So rate law is telling that ethyl acetate and water are involved in the rate determining step, the first step. Del S value, negative value is also supporting that. It is a supporting element. It is also supporting, the negative value is also supporting that it's true that two molecules, when they were free in the beginning, but in the rate determining step, they are coming close to each other, maybe forming a single molecule. That's why its randomness or disorderness is decreasing. That's why its enthalpy is decreasing. Not enthalpy, entropy is decreasing. Entropy, I'm talking about entropy.
So this change in entropy is strictly between the reactant and the transition state, right? And not the product.
Transition state of the rate determining step.
Not the
Rate
product.
determining step.
Okay.
Rate determining step. So this is the rate determining step, right? This is the rate determining step that is supported by Red law. Is it correct or not? We discussed. You can see in the beginning water is there, intermediate one is there, they are free. But in the transition state, they are come closing to each other and forming a single molecule, right? They are coming close to each other, so they are decreasing their entropy. Their randomness is decreasing. They are not free anymore. Water is not free anymore. It is getting restricted. Two molecules are coming close to each other. Okay, so in those cases, you should see the del S will be negative. And this is the actual fact that you got a negative value of del S, entropy of activation. Is it clear?
सर मैं ये चीज कंफर्म कर रहा था कि del S जो है वो हम लोग ट्रांजिशन स्टेट और रिएक्टेंट का लेते हैं या फिर रिएक्टेंट और प्रोडक्ट के बीच का लेते हैं?
No, this is the activation. I'm not talking about thermodynamics. I don't care about thermodynamics here. Regardless, whatever the del S will change here, I don't care. I am talking about only here.
Okay, sir. Thank you.
This is the kinetics. I'm not talking about thermodynamics. This is the activation parameter. You can see this parameter, this one. This is telling this is the kinetic parameter. Okay. So do not confuse about these terms. Okay. If it is del S 0, then that is the thermodynamics. Del S 0, right? Del G 0. There is the thermodynamics. But when this sign is here, this is talking about the barrier. That is talking about the kinetic parameter. Del S in the kinetics. Activation parameters. I'm not talking about the thermodynamic parameter. This is deals with the what is the difference between the product and starting material. Okay, but here what is the difference between the starting material and the transition state, not the product. Do not get confused. Is it clear?
Yes, sir.
Okay, good. Yeah, this is not about thermodynamics. I am talking about the first steps, the rate determining step. Okay, not del S 0. 0 means that is the difference between the product and starting material, thermodynamic parameter. This is the kinetic parameter, has del S of activation. Okay. Okay, one more example. Okay, I already crossed the time. Okay, we will discuss more examples on Monday. I think Monday we have class, right? Anyway. So let's finish this one. So this is also quite interesting. You can see here. So same example I discussed yesterday. T-butyl bromide is reacting with water to give the T-butanol Br minus and water. So obviously, what is the changes of del S? There are 3 molecules, and here there are 3 molecules. Theoretically, it should be del S 0 should be 0. Theoretically, maybe little change. But I'm not talking about the thermodynamic activation and thermodynamic change of entropy. I'm talking about the entropy of activation. So let's see. Let's see here. So this is the SN1 type of reaction that we discussed yesterday. The first step is the formation of carbocation, right? You remember from the last class, carbocation. Then it to give the, this is transition state, and then it form a carbocation intermediate. Okay, then water reacts to the carbocation, give the alcohol. So we discuss about the red law. Red law is telling this is the first order with respect to the T-butyl bromide and 0 order with respect to water. So that means the first step is the rate determining step. This is the highest barrier. This is the highest barrier compared to the second step. And the formation of carbocation is happened in the rate determining step, and whatever the transition state in the first transition state in the rate determining step, that is the formation of carbocation. Okay, so this is consistent with the Reid law. What do we expect for the activation parameters? What do you expect? What do you expect? You can see here T-butyl bromide is actually converting to two molecules, isn't it? The carbocation plus Br minus. Here this bond is getting elongated, right? So it has more disorder, isn't it? Yes or no? Yes, because it is getting elongated. You will get, and at the end you are getting two molecules, Br minus and carbocation. So it is more disorder compared to the starting material. So here, if you do find the activation parameters, then you should expect that del S of activation should be positive or negative?
Positive.
Positive. See, this is the experimental value, plus 12 unit EU. Plus, that is also a very important parameter that will support that yes, this is the possible pathway and this is the rate determining step. The formation of carbocation is happening in the rate determining step. This is consistent with the Reid law also. Is it interesting? Isn't it? It is very interesting.
Yes, sir.
You can also predict.
Sir, please
Yeah.
repeat the positive sign. Why has positive sign?
Hello.
Yes, sir. Can you hear me?
Can I repeat?
Yes, sir.
Yeah, so you can see here T-butyl bromide is what is happening in the rate determining step is the formation of carbocation, right? This is the intermediate and this is the transition state. In the transition state, you can see here the plus, okay, the C and Br bond is getting elongated, right? After it is elongated, then it will break to give
Yes,
the
sir.
carbocation. So when it is breaking, this basically carbon and bromine bond is getting elongated and being broken, right? To give that two ions, isn't it? Two molecules, you may think. So its disorder is increasing or decreasing? It is increasing this disorder, right? So one molecule is actually converting to the two molecules or two ion. They are separated. They are more disorder. So del S, the changes of entropy of the changes of entropy will be positive. Transition state will have more entropy compared to the starting material. Does it make sense?
Okay. Thank you.
Transition state will have more entropy because it is giving the two ion here, right? The bond is being broken. So definitely transition state, they are separated to each other. So transition state will have more entropy compared to the starting material. That's why it is plus. But in the previous cases, your transition state has less entropy compared to the starting material. They are free. The starting material molecules are free, but here they are getting restricted. So that's why it is negative. Transition state has less entropy compared to the starting material. So it is negative. Negative means from starting material to for transition state in the rate determining step, what is the changes of entropy? It is decreasing the entropy, and in SN1 reaction, the entropy is increasing from starting material to the transition state. Does it make sense?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, it's very interesting. Okay. Okay, I will stop. We have more examples. Okay, it is already in the slide. You read it, and then on Monday we will discuss. Then I will go for the Hammond postulate, and then next also. Okay, clear? And at the beginning, I will ask you to ask me any questions. So whatever doubt you have, okay, you ask me at the beginning anytime. But in the beginning, it will be better also if you ask me questions from the previous class. Okay. Okay, so I will stop here. It is 12 o'clock. Okay, and then for the activation parameters, we will discuss more about the examples in the next class. But it is already in the slide, so maybe if you do read in advance, it will be better. It is already in the module.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Please read. Yeah. If you have any questions, you can ask me also. If there is no more questions, then I'll leave. Okay. All right. See you on Monday and happy Dasara. Bye bye.